We are talking about alternating series, and I had just one more thing to say about that, and then we're going to move on to yet another test for convergence. We're getting to the end of the tests. There can only be so many, right? And it can be hard to remember them all. I would like to discuss, first of all, I had another announcement. This is kind of stupid, but for some reason I decided to ask ChatGPT to give me a math joke about alternating series. You want to hear what it said? It said, it was pretty bad. I'm trying to remember. Sorry, I'm going to look. I have the ChatGPT app in my phone, and I'm just going to refresh my memory. I got to get it right. Okay, it says, why do alternating series have trust issues? Because they keep changing their signs. All right. I feel like I don't entirely get it. Like an alternating series does change the signs. Yes. I don't quite see the connection with trust issues or something. Can anyone do better than that? I was trying to think, how could I just change the words a little bit to make it better? I don't know. I thought something about mixed messages, maybe. I don't know. Think about it. I thought we should do this like every time. Make a stupid non joke about each topic. I would like to share with everyone. So this is the last thing that I want to say about absolute convergence and conditional convergence. I hope you recall. So absolute, we say a series AN is absolutely convergent when all that means is just that converges. When you do the absolute value, the series converges. All right? And there's another term, conditionally convergent, which means it does not converge with the absolute value, but it does converge without the absolute value. So we say the sum AN is conditionally convergent. Conditionally convergent when the sum AN converges, but the other one doesn't. The sum absolute value AN does not converge. And there is a very curious true fact about conditionally convergent series that I would like to discuss just in our first 10 minutes or so, and then we'll go on to something else. I thought I would share this with you all just because I think this is not in our book, but to me it's one of the most interesting facts about series that I am aware of. And I don't want to go through the whole sort of detailed proof of this, but this is something you will talk about again if you take our class called Real Analysis, which is a class for math majors that's partially about sequences and series. But anyway, conditionally convergent means the series converges, but the absolute values of it do not converge. And here is so can I say, for example, this is what we talked about this last time, the harmonic series, but with alternating signs, minus a fourth, plus a fifth, etc. I gotta say the dots eventually, right? This is called the alternating harmonic series. This one is conditionally convergent. Because if you add them up with those signs, it actually does converge, but if you change them all to positive, it does not converge anymore. It goes to infinity. All right, we never actually talked about what that converges to, but you can try, plug these numbers into your calculator. Plug in, the first 100 of them and see what it adds up to. This actually does converge to, as a decimal, 0.6931. Anybody recognize this decimal? The answer is probably not, but this happens to converge to the natural log of 2, which is pretty crazy in my opinion. Why should it converge to the natural log of 2? The answer is I don't know, it just does. I mean, you can prove that this is true, but this is not actually what I described before as one of the most interesting facts about sequences and series. But it turns out this thing, if you add these terms up, alternating the signs, it actually adds up to the natural log of 2. All right. What is weird about this is what that means. By the way, you can try to verify this. You could, just like using your calculator, calculate partial sums. And I did this just for fun on my computer. This is not so hard to do, like using Excel or something, or very easy if you're using a real programming language. I calculated the 100th partial sum. That means I just added these up, just the first 100 of them. Not, of course, you can't add together infinitely many of them on your calculator, but if you add just the first 100 of them, I got 0.688 something something. All right. So this value is close to 0.69, which is the true value of the convergence. All right. Though that's the 100th partial sum. Here is what's interesting and, in my opinion, kind of crazy. What if we rearrange the terms? Rearrange the terms in this way. I'm going to add. Now, the original sequence, it has like half of them are positive and half of them are negative, right? And in this way of adding it up, I took the first positive, followed by the negative, then the next positive, then the next negative. What if instead I add 2 positives for every negative? So I take 2 of the positives and then 1 of the negatives. And then 2 more positives. So that's the positive of the odd ones. 1/5, 1/7, and then 1 more negative, minus a 4th, etc. All right? What if I rearrange the terms like that? Now, you should wonder about this. Is this even the same series as this one? So I would say it is, in terms of term by term, this is definitely a different sequence. These terms, the sequence goes 1, negative a half, a third, negative a fourth. Here the sequence goes 1, a third, negative a half, a fifth. So it's a different sequence, all right? But they are the same numbers altogether, but they're just written in a different order. Should you get the same answer when you add them up? Now, if you ask any kid on the playground on these mean streets, they will tell you when you rearrange the order, if you're adding together, when you change the order, it doesn't change the answer, all right? It is not so with series of this format. Actually, if you rearrange it in this way, you can calculate, again, the partial sums of this one. In this case, the 100th partial sum is, I did this morning, 1.039. It's a totally different answer, all right? It turns out this is the very strange fact about series of this type. You can get a different answer by adding the numbers up in a different order. This, to any kid on the playground, this should seem crazy because adding numbers in different orders does not change the answer. This is what on the street they call the commutative property of addition. It turns out, though, it is a fact, the commutative property is true only when adding together finitely many things. But if you are adding up infinitely many things, crazy things can happen, such as this. So this is, this can be summarized. There's a name for this. This is a theorem. It's called, and I'm not going to try to prove this, but just you can tell your friends, tell your moms. I think this is really interesting. This is called Riemann's rearrangement theorem. Rearrangement. And this was worked out by Riemann. Riemann was like late 1800s, I believe. Maybe late 1700s. Sorry to Riemann. I think 1800s. Anyway, Riemann's rearrangement theorem. It says, and it has to do with alternating, like the fact that this is alternating is actually important for this, what I'm talking about, to work out. But anyway, what it says is that if the sum an is conditionally convergent, well, no, let me say it. I'll say what happens if it's absolutely convergent, which that example I was just talking about was not absolutely convergent. But if it is absolutely convergent, then any rearrangement of the series has the same sum. So actually, if it's absolutely convergent, then you can rearrange the terms in any order, and you will actually always get the same answer. All right? But if it's not absolutely convergent, if the sum an is conditionally convergent, that means it converges by itself, but if you were to take the absolute values, it would not converge anymore. If the sum an is conditionally convergent, then rearranging terms can change the answer. Rearranging terms can change the sum. And furthermore, in fact, this is the truly wild thing in my opinion. In fact, given any number, let's say L, we can rearrange the terms so that they sum to L. So not only can the answer change when you rearrange the terms, in fact, the answer can become whatever you want. Given any number, you can rearrange the terms so that they add up to that number. All right? So it's not just like sometimes you can get a different answer. In fact, you can get any answer by rearranging the terms of a conditionally convergent series. This is totally crazy. Like, for example, that means, so this, what I started with was minus 1 to the n times 1 over n. This adds up to the natural log of 2, but there is a rearrangement which adds up to any other number you can think of. So, like, for example, there is a rearrangement which sums to 0. That is possible, to choose the ordering in such a way that all of these alternating signs actually straight up cancel each other out. That is possible. Or there is also a rearrangement which for some reason sums up to pi. So the fact that I got a weird answer of natural log 2 here maybe is less surprising in light of that. Actually, it's possible to add this up to any number you want by rearranging the terms in some weird way. Or for instance, to, you know, my favorite whole number, 8675309. I left out the 3, right? You can rearrange this sequence so that this series adds up to that, exactly that number, right? These are very strange facts, very interesting in my opinion. So next time someone asks you, you know, can I rearrange the order and adding things together, get the same answer? The normal answer is yes, you can. But the more technical answer is, well, actually, if it is an infinite sum of things and they are conditionally convergent, then you will get a different answer if you rearrange the terms. And hopefully they will say, oh, really? What can the answer be? And your answer will be, you can actually rearrange the terms to make it add up to anything that you want. This, to me, is very deep and strange fact. Any thoughts about that? Very strange. I appreciate this kind of unexpected, weird facts about mathematics. That's kind of what I'm into. All right, great. So this was my little cultural moment about Riemann's rearrangement theorem. We will not discuss this again. If you're interested in learning more about that, pay attention during your real analysis class, like when you're a senior or something. All right, great. Let's move on then to the next test. This is the last section in our book about convergence tests. I don't know if you're sick of these yet, but this is going to be the last one. There's one called the ratio test, and there's one called the root test. They are both kind of similar. Once you know how to do the ratio test, the root test is like, oh yeah, you can also do this other thing, and that's a slight variation, which gives you the root test. We'll mostly talk about the ratio test, but the root test is also there. Unfortunately, to me, I find it a little unfortunate that there is something called the ratio test because we already have the limit comparison test, which is about doing ratios. That's not this. So there's this other thing called the ratio test, which is also about ratios. This is our last sort of series convergence test, and then we're going to go on to something else to discuss. But it's based on the idea of, let's say, a geometric series is one in which they have these common ratios with each term. I hope everybody remembers, for instance, this is a geometric series. This is geometric. With a common ratio. That's what it means to be a geometric series. It means that each term has the same ratio with the previous term. And of course, I hope that everybody remembers, the series will converge. Well, I'll call this R here. And then it converges. How do you know when it converges according to R? When R is less than 1. Yeah, right. Everybody knows that. The series converges when R is less than 1. Now, the ratio test is a variation on this, but what if the R isn't quite the same every time? Right? Like this one, it is actually straight up the same every time. If you divide each one divided by the previous one, in this case, the R is 1/3. And it literally is always 1/3. But what if it's a sequence where you don't always get the same thing, but maybe like they're all kind of similar to one another? Like what if you get different ones, but they're all less than 1? Shouldn't that still converge anyway? Even if they're not the same every time, what if they're all different, but they're all less than 1? This is the kind of the idea behind the ratio test. What if the common ratio is not exactly common, but what if it is something else? So the idea is you want to check these ratios, an plus 1 divided by an, right? It's always the next one divided by the previous one. And generally speaking, they're not going to be the same every time. But if they are slightly different every time, you can still come to more or less the same conclusions as in the ordinary geometric series. So I'm going to write this as a theorem, and this is called the ratio test. And it says, here it is, for any series sum an is what we're looking at. First of all, this has sort of 3 parts here. I'll say it this way, lim n goes to infinity. You look at these ratios in their limit as n goes to infinity. That you imagine is like the R from a geometric series, although they might not actually be the same every time. It doesn't matter if they're the same every time. What matters is that eventually these ratios tend to be the same amount in the limit. All right, so if that, I'm going to call this L, which is playing the same role as the R from before. But anyway, if that L is less than 1, then the series converges, just like a geometric series. And in fact, you can say even better than that, then the series is absolutely convergent. So this test not only tells you that it converges, but in fact that it is absolutely convergent, which is a little bit stronger. It means it converges, and also it even converges if you were to take the absolute values. All right? So if this quantity L, which you should think of as being like the R, if it's less than 1, then the thing converges. If it's greater than 1, it diverges. That's what I'm going to say here. If this whole thing, L, is greater than 1, then the sum an diverges. The unfortunate case is, what if it equals 1? So actually, I really like the ratio test because it requires no creativity. Like our other tests, the comparison test, and even the limit comparison test, You have to think up another thing that you're going to compare the first one to, and you just have to make it up, the other thing. Here, there is no other thing that you have to invent. You just take the series that you're given, and you do this ratio here. So the downside of this test is the third part here. If this L, the same L, that limit, happens to equal 1, then the test is inconclusive and we don't know anything. We don't know. So, I mean, if you're really trying to figure out if it converges or not, you just have to use another method in this case. So the ratio test does not require any creativity. You don't have to make up some other thing to compare with. And so in that sense, it's more straightforward to use, but it has this sort of failure case. Sometimes it just straight up doesn't work, and you got to do something else. All right? Anyway, that is the ratio test. Let's just do a couple examples, and then I'll tell you what the root test is, which is a simple variation of that. Let's try some examples here. Another nice thing about this is you don't have to know ahead of time if you're trying to show it converges or not. So you can answer a question like, does it converge? What we're going to do is find that L, and then if the L is less than 1, yes, it does converge. If the L is greater than 1, no, it doesn't converge. And that's all there is to it. If the L equals 1, then you're kind of screwed. So hopefully that won't happen. All we got to do is we'll find the L. All right, so I go, L is lim, n goes to infinity. Usually you can just sort of directly work this out. an plus 1 over an. That's the L that I'm talking about. And then you kind of, plug stuff in, simplify as much as you can, and try to take the limit. This will sometimes involve L'Hopital's rule at the end, but we'll see what happens. So an plus 1 means I go, an is this. An plus 1 means I write all of this but using n plus 1 instead of n. So it'll be n plus 1 over 2 to the n plus 1. That's an plus 1 on top divided by an. That's just n over 2 to the n. All right, we have to simplify this. Sorry, I should have written lim again there. I didn't do the limit yet, of course. All right, to kind of straighten out this double fraction, I will write it as multiplying by the reciprocal. So this is that times 2 to the n over n, right? And then simplify as much as you can. I would say the 2 to the n and the 2 to the n plus 1 can cancel, and that's just 1/2, right? There's an extra 2 on the bottom. All of the other 2's will cancel. Sorry, I forgot my lim again. One half, and then the rest of it is n plus 1 over n. And what is the limit of that? The 1/2 is just going to stay, like it is, 1/2. Can anyone say, what do you get from n plus 1 over n? Show me the fingers. The answer is 1. Yes. If I ask for the fingers, probably it's 0 or 1, or sometimes 2. But anyway, it's 1 in this case. This is, of course, a ratio of polynomials of the same degree, and so you look at the coefficients on the top term, which is 1 over 1 in this case. All right. Anyway, so L is less than 1, so it converges, and that's it. Very nice, in my opinion. It's usually fairly straightforward to work these out. Any questions about what we did there? Just to make sure you don't get the fractions all mixed up when you're making them fractions. All right, let's just try one more. How about some... unlike the comparison test, this one does not require that the series all be positive. So I can do this even on an alternating series or some series with weird terms in it. It'll be fine. Minus 1 to the n, e to the n over n to the power 8. All right, we don't have to, don't get too excited thinking about this. Let's just try to calculate this L. It is lim n goes to infinity. an plus 1 divided by an, right? Maybe I can just try and write this as multiplying the reciprocal immediately. So I'm going to do an plus 1 first. That would be minus 1 to the n plus 1, e to the n plus 1, divided by n plus 1 to the power 8. I don't like that too much, but hopefully I won't have to actually expand that out. That was an plus 1, and then I'm going to do times the reciprocal of an, which is this. But I'm going to do the reciprocal. That would be n to the 8 over minus 1 to the n, e to the n. All right, that is an plus 1 times the reciprocal of an. It's the same as doing that division. Simplify as much as you can here. What do we get? We can kind of try and simplify. Okay, I have negative 1 to the n plus 1 divided by negative 1 to the n. These will all cancel, leaving 1 left over. So this is going to be, I think, just a minus 1 left over, right? And then the e's. I got e to the n plus 1 over e to the n. What is that simplified to? Just e, yeah. N of them will cancel and e remains. So e, like e to the 1 if you like. And then I'm going to write those out front. And then we have the n's, and the n's actually don't really cancel nicely here. You can't really do much with that, although, so it's n to the 8 over n plus 1 to the 8, right? I would say one thing you can do is minus e the number, times, here's one way to simplify that a little bit. That's a little easier to manage in this case. All right, and now we're going to take the lim n goes to infinity. So the minus e will just be, I mean, that's just the number e, whatever that is. And then this, what about n over n plus 1? In the limit, that approaches 1. And so this is going to be 1 to the power 8. Again, this is 1 because it's a ratio of polynomials of the same degree with the same coefficients. So I get minus e times 1 to the 8. And my answer is minus e. Why is it minus? Oh, you know what? This is bad news. I'm sorry. Oh, this is real bad. It's not so bad, but I feel ashamed to have made this. I made an error, and it's right here. The theorem requires absolute values right there, which almost never matter. They matter in this example I was just doing. Sorry about that. So go back and put some absolute values here. All right. It's because of the alternations. Like the alternations can make weird things happen with the L's here, and I don't want to have to consider what happens when L is a negative number. So going down here, what I should have done in this example, the previous one, was absolute values here, which don't matter because everything here is positive. So these absolute values have no effect. They do have an effect here, though. I'm sorry about that. So here should be absolute values around this whole thing, and I would put absolute values here, which just amounts to making this positive everywhere. Positive e is the value of L in this case. I'm so ashamed of forgetting the absolute values. All right. This is why nobody asked, the theorem says if it's less than 1, or if it's greater than 1, or if it equals 1. What about if it's 0 or negative or something like that? The answer is it never will be because of the absolute values. But, yeah. All right. Sorry about that. Anyway, it is e. Is that greater or less than 1? Anybody happen to know what e as a number is?
It's greater. It's like 2 point something.
Yeah, it's 2 point something something. That's about all I know about what e is. Anyway, it's greater than 1 though. So this e is greater than 1. So that means L is greater than 1, so it diverges. Right? It diverges because the L is greater than 1. All right, I thought, can we just do one more quick example where the L equals 1? I just want to show at least one time where that happens. And unfortunately, it happens sometimes just in very simple examples. Like, how about this? Now this example, you should not really have to use any of the tests. If I ask you if this converges or not, the answer is it does converge because this is a P series with P equals 3. So this is P series, P equals 3. 3 being greater than 1, so it converges, all right? But let's pretend that we didn't know that. What if instead of, this is a basic fact that everybody should know, but what if we just tried to use the ratio test on this? If we try ratio test, what does it look like? I do the L thing. L is the lim, n goes to infinity. I'm a good boy now. I put the absolute values like so. All right? They're not going to matter here because the terms that I'm going to be plugging in are all positive anyway. But you ought to write that absolute value signs at least in the first. Anyway, I get a n plus 1. That would be 1 over n plus 1 cubed times the reciprocal a n would be n cubed over 1, I guess. Right? This is a n plus 1 times the reciprocal of a n. And then this I will simplify the way that I did in the previous one. That would be to write it like this. N over n plus 1, the whole thing cubed. And then again, this limit goes to 1. It's like 1 cubed, right? When I do the lim. That fraction part becomes 1. All right, so L equals 1. So we can't conclude anything. From the ratio test. All right. Of course, we know for other reasons that this thing actually does converge, but the ratio test is not able to detect the convergence of this thing. All right. This is the ratio test. I think it's fairly, easy to use. You just sort of plug stuff in and work out the limit. Maybe I have some for you all to try, but could I just tell us about the root test? I said before, the root test is a simple variation on this. So the root test, and then I'll have some for you all to try, which are just kind of combinations of ratios and root tests. The root test. The root test. So this is in structure very similar to the ratio test, but instead of taking ratios of one term to the next, you use weird roots. I'm just going to write it down, and then I'll talk about what this comes from. Although it's easy to use, just like the ratio test is. It says if it's a similar thing with like a L that comes from a limit, but the limit this time is like this: lim n goes to infinity, nth root of absolute value a n. So this involves not doing one term compared to another term, which is the ratio test. This is just each term by itself. You take the nth root, which I don't know about you. Usually I don't like taking the nth root of things just because it's complicated, but sometimes this is actually very convenient to use. Anyway, if you call that L, and then all the same sort of rules are true of this thing. So if L is less than 1, then it is absolutely convergent. If that same L is greater than 1, it diverges. And if L equals 1, you don't know. All right. Why should you believe this? I will give you just we don't need to talk about this in huge amount of detail, but why? It's basically because if I say nth root of a n approaches L, this is the same as saying a n by itself. Sorry, I meant to say approaches with a little arrow. Another way, if I just kind of like do the nth power on both sides, this is similar to saying an sort of approaches L to the power n. If I take this over here and do the nth power on both sides. And what that means is basically, so an is like a p series because what the terms individually look like are various powers. It's like the first term looks like L, the next one looks like L squared, the next one looks like L cubed, and so on. And so the AN is like a P series, and if the L is less than 1, it's going to converge, and if the L is bigger than 1, then it will diverge. This is the basic idea behind the root test. But when you're using the root test, really, you don't need to remember any of this business. You just need to remember how to set this up and to take the various limits, and all you got to show is that that limit is less than or greater than 1. So when would you want to use the root test? This, to me, like I said, I almost never want to take the nth root of anything because it's so weird. But there are certain sequences where you will want to take the nth root. So I will say use this for sequences where you see nth power. For example, the sum n plus 1 over 2n to the power n, all right? Here I have an nth power and some other stuff inside of it, but actually that is something which gets simpler when you take the nth root of it. And so I'm going to use, I see this nth power here. That's my tip-off to use the root test. So my root test setup will be L is the lim, n goes to infinity, nth root of absolute value an, right? It's just a single term. You don't do a ratio. There's no divided by n plus 1 or anything like that. It's just an. Exactly. So this is nth root. Just plug that business in here. The absolute value doesn't matter because everything is positive, so I can ignore the absolute value. It's like that. And then what happens with the nth root? The nth root cancels the nth power here. And this thing just ends up equaling lim n goes to infinity, n plus 1 over 2n. The nth root cancels the nth power. This is why I said you use the root test for sequences where you see an nth power, because then when you take that nth root, it will simplify everything for you. Can somebody shout it out? What's the limit going to be of that? 1/2. 1/2, yeah, because this is, again, a ratio of polynomials of the same degree, and I use the coefficients on top, which is a 1 on top and a 2 on the bottom. So that is 1/2. And so, just to conclude, so L is less than 1, so it converges. All right. Without the root test, I would not really know what to do with this. I mean, this is a very complicated, weird thing with the something with n's in it, also to the nth power. Very strange, but it works out great using the root test. All right. Okay, I got 3 for you here. I would like you. Maybe I'll give you 2 here. So you decide for each one. Should I use the ratio test or the root test? All right, so show if it converges or not for each of them. Now, it may be that you could use either the ratio or the root test, but I will let you decide which one seems more appropriate. Feel free to chat with your friends if you like.
Yeah, yeah. Maybe.
Anywhere? Yeah, this looks pretty good.
I would say this is something you can leave together and divide by n plus one. That's one thing. The other thing could be n plus one over. We can't for this. And then what remains here is n plus one divided over n. Like in that thing, you can just divide out and say it's a fraction.
It's similar direction. Well, basically, and this is one half. Oh, 17.
Oh, yeah.
So,
This piece can cancel.
so they can, zero, two,
These ones, you can cancel.
zero, and this is zero, two.
This is like you could.
Yeah, one, yeah, one compare those two, that goes to geometric series.
Subtracting.
Because this cancels out. You just plug in the inequality, so it's a piece of equalities. So, zero, I think the start of this, when we're subtract this.
Yeah, negative. So it's a single two on wow.
The max, so there's two geometric series, which then,
Yeah, it's just one.
goes to zero. So it's
You can do that then.
Where are you using inequality?
It says you must.
But like, where are you getting from your
Oh, because of 1 plus cosine x is boundless. Yeah, between 0 and 2. That's what we see. So the series works. Kind of did. It's because like it's all like fancy just my friends see it.
Somewhere?
Oh yeah, you can expand this. Cancels
So then that.
Oh, you expand it everything?
Well, no,
Oh,
yeah,
k minus 1k.
yeah, and then this goes to k over 4, and it's like k squared. And then I think that just was the combinators.
So you just took the one.
Yeah, limit comparison. 16.
Then you have to compare.
16. A P series connects.
Here?
Cancels out. And then it's
Yes.
and still power and P series. The K is power.
All right, we're gonna go in a few minutes. Maybe we can just do these. I saw people doing great all around. So the first one, I used the ratio. And that means I have to do lim n goes to infinity of absolute value. So it looks like that's the n plus 1 term, and then times the reciprocal of the n term, which is 2 to the n over 3n to the 5, right? That's what you should start off with, and then simplify this. So I can straight up cancel the 3's, that's the easiest thing. And then I have 2 to the n up top, 2 to the n plus 1 on the bottom. That means I have, this is 2 times 2 times 2. There's n different 2's up here, and n plus 1 different 2's down here. So that all of these 2's can cancel, except there will be 1 left over in the bottom. So this will look like still lim. Absolute values don't matter because it's all positive. I have an extra 2 in the bottom, and then what's left over is n plus 1 to the 5 over n to the 5, which I'm going to write like this. Whoa, not like that. This is a similar trick that I used in a previous example, and that's a common thing that you're going to do in these types of examples. It used to be n plus 1 to the 5 over n to the 5, but I made it into that. And the purpose of doing that is that now I can take the lim, and this part inside, its limit is 1, because it's a ratio of polynomials. So I get 1/2 times 1, which is a half, so it converges, because a half is less than 1. Right. Some tricky simplifying in there, but hopefully it worked out. And the other one I used the root for, so just real quick, the root test on that is, so I'm going to do the root here, lim nth root absolute value 5 to the n over minus 2 to the n, right? And what I would do with that is sort of re-simplify the inside there to pull the nth power out. So it'll say lim of nth root of nth power 5 over 2 to the n. And again, taking the absolute value can just change the minus 2 into a plus 2. And now the nth root cancels the nth power, and we are just left with lim 5 over 2, which of course is 5 over 2, and that's greater than 1, so it diverges. That's that. The ratio and the root. There's not a lot more to say about these, but maybe we'll do a couple more examples next time. I hope you all have a good weekend, and I will see you on Tuesday.